Hello grade 12s, this is part 2 of our equilibrium law lesson. We have 3 examples left to complete. These are examples 5, 6, and 7, each of which are very different from each other but still about equilibrium law and specifically calculating, at least for the first 2 examples, our KEQ value. So KC is what's being asked of us in example 5. KC is just the same as saying KEQ. Except that C specifically means the K value for the certain concentration of given products and reactants. So we'll get to that first. Then KP, where P stands for pressure, which we're basically calculating again the KEQ value, but for a pressure system instead, so something involving gases. Question involving gases. And example 7, here we're not calculating KEQ. Here we're given our KEQ value, we're going to calculate the concentrations of our products and reactants at equilibrium. Okay, so let's just scroll down. I believe it's here. Okay. So example 5, I've highlighted what's important here. So it gives you a balanced equation. Always make note of that. Make sure it's balanced. Okay, so here it says you're going to calculate our equilibrium constant Kc, right? Again, it's the same as saying KEQ at 25 degrees Celsius, and you'll see a lot of these questions will give you a temperature measurement. It really has no bearing on how you're going to perform the solution. It's just, again, reminding you that these K values are temperature constant or temperature dependent. So this whole equilibrium situation here exists at or occurs at 25 degrees Celsius, but really no bearing on the question. So enough of that. So for calculate Kc for the reaction using this information. So here we have 2 moles. All right, well, first you have to calculate concentration. I believe that is our first step here. So you have moles of NaCl, okay, reactant, and that's placed in a 1 liter flask, right? So that concentration value is pretty simple, remembering that concentration is moles divided by volume, and the concentration of NO, right, not nitrous oxide, as a product at equilibrium is achieved at 0.66 moles per liter. Okay, so not too different from what from the previous examples we've done. Here we're just calculating our Kc, in this case, given a concentration at equilibrium. So hopefully not too challenging since it's similar to what we've done in a couple of previous lessons ago. Okay, so as always, you begin after you've calculated concentrations, given concentrations, in this case pretty simple, moles divided by 1 liter is a 2 molar concentration. Then you create an ice table. Okay, so your initial concentrations given or calculated in this case is 2 moles per liter. Initially nothing's reacted, right, at time 0, so we have 0 concentration for products. Then we can write expressions for change. We know that they're proportional to the coefficients in the balanced equation, so you write negative for the reactants since they're going to be consumed. Include that 2 because they're consumed in that ratio, 2 to 2 to 1. Well, not consumed 2 to 2 to 1, but they exist in 2 to 2 to 1. Now products, NO is going to be produced. We get a positive X value here, and it'll be 2X because this concentration is changing by value 2X, increasing because they are products that are going to be produced. Same here, except the coefficient here is 1, so that means it's just X. All right, so here are our expressions. Again, all you're doing is you're adding I and C. Right, I and C give you E. Right, here's the I, here's the C. You add them together and you get E. So 2 minus 2X is that expression here. This represents the equilibrium concentration for our reactants. 0 plus 2X is just 2X. Fortunately though, the question, it tells us what the concentration at equilibrium is, so it's 0.66 moles per liter. That makes it quite simple to figure out what X is, right? Just divide by 2, and I do that off to the side here. Okay, now chlorine as well, it's I plus C, C being X, it's just X. Okay, so here's that simple algebra. So from the table we have NO is equal to 2X, and that's equal to 0.66 moles per liter. So to figure out what X is, you divide both sides by 2, and we now know the value of X is 0.33 moles per liter. Okay, so that, and I'll do the work in the next slide, but that allows us to solve for the concentration of chlorine, and of course we already know this value, so that's okay. And now that we know X, we can figure out what NaCl is. Okay, so that's the next thing we do. Okay, so plug in, substitute, you know what X is. And here we are, we get a 1.34 molar concentration of NaOCl, our reactant, and we know that X is 0.33. With these known values, together with a known value given to in the question of our other product, we can plug that into our KQ expression or KC expression. So that looks like this, remembering that the coefficients are the exponents and it's always products over reactants. Also double check. It should, in the question, either explicitly say here, as it does, or in the question it should say. So here we're looking at concentration of gases, and we know that as gases, as we change amounts of gases, we also change our concentration. So you're essentially looking for anything that is a pure liquid or a pure solid. If those appear, you know not to include those in your expression, your equilibrium expression, but because they're all gases, we do. So our expression is this. I plug in, substitute our now known values, our now known concentrations for each of these, and we get 0.66 to the power, or to the exponent of 2, times 0.33 over 1.34 to the exponent 2, and this is our Kc value. Okay. Another step to this question, although it doesn't ask, it could say what part 2, or part B, let's just say, given the solid K value, what direction does this reaction favor? Okay, so hopefully you're thinking about this. Now this is less, notice that this is less than 1. All right, so Kc is less than 1. Okay, so that means our denominator here, this is a greater number than our numerator is, which is our products. So I'm hoping you're thinking that this is now favoring the reactant side, which means it's favoring the reverse direction. Okay, so that's the answer to that. Okay, next question. So this is a different question, different sort of question, and we have to look at this reaction a bit more. Well, always look and make sure it's balanced, and look for solids or liquids. In this case, we have a solid, right? So make note of that. And it says when solid ammonium carbonate sublimes, it dissociates completely into ammonia. Here's ammonia and carbon dioxide according to that equation here. Okay, make sure it's balanced. It appears to be balanced, so that's good. Again, you see a reference to a temperature reading, has no bearing really on solving the question, so you can ignore that. Experiments show that the total pressure of gases at equilibrium or in equilibrium with a solid is 0.116 atmospheres. What is the equilibrium constant Kp? All right, so this is new. All right, so we have a total atmospheric pressure. Now, notice I didn't last time, and I won't now read through the method on how to solve these kinds of questions. I think you can do this yourself, and it's best to refer to this step-by-step method on how to solve when you're working through your own problems, through your own questions. But we're going to jump right into it, where we can put into context. Okay, so here's our ICE table for this reaction, for this balanced reaction. Notice that because this is solid, we don't write anything for that. Instead, we're focusing on our products here. So initially, what do we have for concentrations of our products? As you would suspect, it should be 0. Nothing's happened. At time 0, we still have a solid reactant hasn't sublimed yet. We have no amounts of products. Okay, but that will change proportional to their balanced coefficients here, where our products are positive x's, so we get 2x, and here we get just x because of the 1 here. Right now we add I and C, and we get 2x, and here we also get x. But think about what this means now. So in a gas, if you recall grade 11, okay, so Dalton's law of partial pressure says that the individual pressures of the individual gases that exist in a system, if you add them all up, the sum of all those individual or partial pressure will give you the total pressure. So what that means is if you add this, wrong pen option. Okay, so if you add ammonia and carbon dioxide, you add these two, they give you a total pressure. Now back to the question, it gives you this total pressure. It says that the total pressure of these gases at equilibrium is 0.116 atmospheres. So again, this is just Dalton's law of partial pressures, the individual partial pressures of gases. Add them all up, they give you the total pressure. Okay, so let's do that. Knowing that the individual pressures of ammonia and carbon dioxide, we have expressions for those, right? 2x and x. We also have this value given to you from the question. You can create a linear equation that can be solved algebraically. So 2x plus x is 3x. You can then figure out easily then what x is. Okay, so this is our value for x. And because of that, we can now plug this value into our ice table, last row in our ice table. Okay, so this is the expression for the partial pressure of ammonia. We know what x is. We therefore now know what the pressure at equilibrium for ammonia is, 0.07734. Again, try to keep at least 4 or 5 digits, don't round. And we can first figure out the last one for carbon dioxide. It's just x, and we know the value for x. So this is the pressure at equilibrium for carbon dioxide. Okay, so great. We now know the partial pressures of all of our species, but it's not asking us for that. It's asking us for Kp. So that means we need an expression, an equilibrium expression. This looks kind of funny, doesn't it? This doesn't look like your typical KEQ expression. A couple of things are happening here. Notice we don't have a denominator because that would be referring to the reactant, which is solid, so you don't include it. The other thing is this doesn't involve concentration, which you're used to, right? This is the first kind of question you've seen of this sort. So we know these values; these are the partial pressures, right? Again, continue to follow the rules as we've seen before, where exponents they come from the balanced reaction and their coefficients. So plug in our now known partial pressures of ammonia and carbon dioxide. Plug those into the correct exponent, and this is our value. So Kp. There you go, 2.31 times 10, and I'm pretty sure this is a negative, although it's hard to see, but this is a -4. Okay, so that's our Kp expression. Okay, quite small, you should be able to figure out then what side it prefers, left or right. Okay, number 7. I have most of 7 already solved for you, but I thought this question, yes, you just saw that, right? You recognize what that is. I thought let's go through this question ourselves. Okay, but first let's read it over. Actually, I copied it here. Okay, so example 7. We have a sample of 0.00 moles of fluorine, okay, fluorine gas, that was sealed in a 2-liter reaction vessel, right? So we have again moles, and here I need to switch to a pen. We have moles, but we need to find out what concentration is. So we have moles, we have volume, right? Again, C is equal to M over V, and we can figure out what concentration is, right? And that's heated to 1000 Kelvin, right? Again, another reference to temperature, that's great, but we don't need that. To study the dissociation of fluoride or fluorine atoms. At this temperature, Kc is that, great, so we have our Kc value. What are the concentrations of our reactant and our product at equilibrium? And there's another part to this, what is the percent dissociation of F2? Okay, so let's start. First thing you should always do, make sure that you have, wherever you can, expressed any values expressed in concentration. So let's do that now. Right, so F, concentration of F2 at time naught, or initial concentration, is 0.0020 moles. And we're going to divide that by, scratch that, 2 liters, which gives us 0.0010 moles per liter, or that molarity. Okay, next step is your ice table. Okay, just like in grade 11 where the mantra was when you don't know what to do, or even if you do, always figure out the number of moles. In this case is for equilibrium, when you don't know what to do, figure out or draw an ice table. Okay, so your ice table. So I, C, E, all right, and then our balanced equation, just going to rewrite that. I'm using that double half arrow you've seen before to F. Okay, so from our work just over here, I'm going to plug this in 0.0010. We know that this is concentration, so I'm just going to leave this, leave units out of this for now, knowing that this is referring to concentration. Right, and at time 0, we have no no product exists, so we have 0 concentration. Okay, now write in your known expressions for C. We know that this is going to decrease by a negative value, an unknown x, but proportional to the coefficient, so it's minus x. Our product is going to increase, so positive x, but it's going to increase proportional to that coefficient, so it's 2x. I plus C gives you an expression at equilibrium for reactants, 0.0010 minus x, and we get 2x for our product. Okay, so we have expressions at equilibrium for both substances. Now it's asking us to figure out what are the concentrations of these substances. So we're going to have to figure out what x is. Okay, so what we know so far is that we have a Kc value of 1.2 times 10 to the negative 4. Okay, we also can, from here, can figure out that we can write a equilibrium expression, right? Products over reactants. Right, so this is our expression. We have expressions for these individual concentrations, and they are here. Just plug them in, right, straight from your ICE table. So 2x squared over 0.0010 minus x. Okay, I'm going to simplify this a bit, just expand slightly. And we get 4x squared over 0.0010 minus x. Okay, good. So my math form isn't here. I should continue left to right or top to bottom, not go around. But I'm going to just plug this now here. We know that this value is 1.2 times 10 to the minus 4. Okay, we have to solve for x. So let's expand. Okay, let's expand. So I'm going to cross multiply, and we're going to get, right, there's an imaginary 1 over here, so it'll be okay. Now, how do you normally solve? You learn in grade 10, in your grade 10 math class, how do you normally solve for an equation that looks like this? There is an x squared variable, there is an x variable, there will be a constant if you expand this, right? So this looks like a quadratic form, or can be. So we need to write this, expand this out into the dreaded quadratic form, and remember that to be ax squared plus bx plus c is equal to 0. And once you have it expanded in this form, then you can plug that into your quadratic equation. Okay, so we'll have to do that. Back to your grade 9 math class, you're expanding properly here. So this times that, this times this, bring this over to the other side, make this side 0. It will look like, let me just do it over here, it will look like this. Your quadratic form is, that is times 10 to the negative 4 minus 1.2 times 10 to the negative 7 is equal to 0. Okay, so this is now your a value, 1.2 times 10 to the negative 4, and I'm missing an x here. Okay, this is your b value. So this is a, this is b, and this negative 1.2 times 10 to the negative 7, that is c. Okay, with these known values, you can then plug that into your quadratic equation. Just going to scroll down to give myself some room here. Now I know a lot of your fancy calculators have a quadratic calculator built in it. All you have to do is type in your a, b, and c values in it, and it shoots out your x values. Okay, because this isn't a grade 10 math class, and I'm not testing how you can input into a quadratic equation. You feel free to use that. Okay, knowing, however, what this means. So x we know to be a positive or negative value. Our quadratic equation really is negative b plus or minus the root, and that root is called something. I forget what it's called. It's a determinant? I can't remember. All right, but here's our quadratic equation. Okay, we can plug in our a, b, and c values, and we get negative 1.2 times 10 to negative 4 plus or minus okay, all of that, and draw a straight line, all of that over 2 times a, which is 4. Okay, so because of this positive and negative, you're going to get two values. So go ahead and solve this. I'm not going to take my calculator out and solve this for you. What you will get, though, are two values for x, as you would for the solution of a quadratic. So your positive x value, if you use this operation, the positive sign, is going to be 1.59 times 10 to the negative 4. And your x negative value is going to be negative 1.89 times 10 to the negative 4. Okay, now you have to consider what this means. This negative value of a solution to this quadratic doesn't make sense. It's not possible. Look back at your ICE table. If you had a negative value for x, you would have a negative concentration for fluorine. Negative concentrations are not possible. So because of that reasoning, you can then say that you're going to ignore the negative x value. Okay? This won't always be the case. Usually it actually is. You won't always have to ignore that negative value. Always refer back to that last row in your ICE table. Will that make any concentration negative? If it does, then you can ignore it. And although it may usually be your positive x value, which would be the real answer, the real solution, don't always and so freely dismiss the negative value, because sometimes it's not. Okay, let's change back to a black pen. Okay, so now that you have our x value, figuring out what the concentrations of everything else is a bit more straightforward. You have expressions for everything at equilibrium for the two substances. All you do is plug in your now known x value. Okay, molar concentration last. Should be concentration there. Okay, that is 2x, right? You know what x is. Negative 4. Okay, molarity. Okay, that's usually where the question would end, but this one had an extra part to it. Doesn't that make you happy? So it says percent dissociation. What is your percent dissociation? So essentially that's just the amount associated. So over your given or your initial amount. Okay, times 100. All right, so putting this all together, we then have our percent dissociation is going to be our x value, right? Back to our ICE table to see why I chose our x value. Okay, so how much really dissociated of F2, and then how much do we initially have of F2? Oh, just notice though, it's not just 2x. It's not just 2x. Okay, so it's this expression here. So how much did we have at equilibrium? right? 0.0010 minus x, which we know to be, let me just change this first. It's not x here. Okay, it's from our expression, but I won't even need to write that full expression because we know that concentration already. Where is F2 at equilibrium? Oh, down here. Okay, so F2 at equilibrium 8.4 times 10 to the minus 4. No. How much dissociated? Let me go back. Okay, it is this. I can just write. Oh, okay. Sorry guys, right here, 2x, how much actually dissociated? Okay, that makes sense. It's getting all mixed up there, right? So 2x. Okay, and that we know, right? That is right here. Okay, so that's 3.2 times 10 to the negative 4. And how much do we actually have? Initially, if you recall, 0010, we multiply that by 100. Okay, and we get approximately 31.8% is what I calculated. Okay, so amount associated, there you go. Be sure to choose a correct value here. All right, hope this helps. Your home fun is here. Okay, give it a try in case you need any background reading. There you go. Page 436, questions 1 to 3 and 5 to 6. There is also lots of extra practice on our website on Teams.